Okay, so our sixth point, and this application of first law of thermodynamics is nothing but the boiling process. So previously we have studied about different five applications, which were isothermal process and adiabatic process, isovolumic process, cyclic process, and melting process. So today we will discuss about boiling process. So during boiling, we will consider that uh, the liquid is converting into steam, and during this, the temperature remains constant. So when the liquid is turned into the steam, the volume expands. Basically, the steam covers more volume than the liquid itself, but the mass almost remains same. So in this liquid case, let us consider m to be mass and pressure be p and volume let it be v1 in this case. So this would be volume, and for steam case that all should be same, but the volume let it be v2. Why we are taking pressure to be same means the as the boiling takes place, the piston is moved upwards, so all the work is done in only during the expansion. So pressure is almost constant. So P is also the pressure here, and M is the mass. Okay, so we will move on to the next. Then let L be the latent heat. Since the boiling process is taking place, so L here will be considered as latent heat of vaporization. So overall work done, so total work done in expansion is equals to dW. Let the work done to be very small, but P dV the same. This dV can be written as P V2 minus V1, since the volume 2 is X more as compared to the liquid volume. So during this process, all that heat that is absorbed by the liquid and that is converted, that is making it to convert towards the steam, that could be considered as dq is equals to ml, and according to first law of thermodynamics, this could be written as dq is equals to internal energy plus work done. So putting all the values, we can write this as ml, and this du plus p v2 minus v1. So rearranging, we get internal energy to be same, since there is no such variations we can say, because in all the conditions pressure is remaining constant, only the expansion is taking place. So rearranging ml minus p v2 minus v1. So if this could be known, the volume could be known, the mass, latent heat and pressure is already known, we can calculate the change in the internal energy of the liquid when it is converting to the steam or the vaporization process. Okay. Now the next application, since we have discussed about specific heats, the steam process has been coming on. Now we will discuss the very important point, one of the very important point that is Mayer's formula. This is nothing but the relation between two specific heats of a gas. So we need to discuss this since it may be an important topic as per your exam also. So be prepared and looked this very carefully. So let us discuss about this thing. First of all, that we know that first law of thermodynamics can be used, uh, means all this relation can be used and can be prepared by use of first law of thermodynamics. So for this, let us consider the amount of gas first of all, so that we can take a specific amount of gas on which we are doing some research and on which we are trying to relate the equation, relate the finding out the relation between these parameters. So let 1 gram be 1 gram of mole of ideal gas could is taken. So we have discussed also that what is an ideal gas, what are the properties of an ideal fluid also, and in this case it is enclosed in a cylinder. Okay, and the cylinder is nothing but is filled in a piston. Let us assume it with help of the diagram so that it can be clearly understood. So this is the cylinder and the piston condition. Let us consider, and thus this piston is frictionless since no loss of energy, so that we can assume that all the energy is being transferred from one form to another. Okay, so in all these cases, let P be pressure, V be the volume, T be the temperature. Means all these things are initial conditions. Okay, if the gas is being heated, let us say that the gas is being heated, so what do we observe, that this a little expansion takes place and this pushes this piston upward a little. Let this be shifted in this manner. So there is a little shift, a little upward shift, and that is this time, this duration. Just a small displacement has been made. Sorry. So, in order to look for this change in temperature, that change in temperature, let it be dt. So what could be the amount of heat that is transferred to the gas? For calculating that, and also we have taken mass to be 1 gram already. Mass has been already taken as 1 gram. So amount of heat, that is Q. So amount of heat dq is equals to mc delta t, that we know that Q is equals to mc delta t, but m is 1 and c is at constant volume. First of all, let us say, because at constant volume. So volume is constant, so we can write it as cv into dt. So let this be an equation 1. So what is this cv? We can write this as specific heat at constant volume. Since it is considered, m is considered to be 1, let us mention it for clarity. And since dv remains 0, since the volume is taken to be constant, therefore dw, what is the work done now? Again, the work done is 0 since no displacement has been made and the volume is kept constant. So in this case, by first law, dq is equals to du plus dw. dq we have solved it here. dt is equals to du and dw is 0. So we can write this as du is equals to, or du is equals to cv dt. Now at the second condition, let the gas is heated at constant pressure, means volume is not changing this time. This time we are keeping the pressure constant. So let the gas be heated on, we can say at, it should be at constant pressure. So at this condition, what is the amount given to the gas? So amount of heat provided, that is dq is equals to, let it be dq dash, so avoid confusions, and mc delta t same, m is 1, c is p, cp is here, and dt. Now this could be taken as another equation 2. So we can write this as work done, amount of heat provided is dq dash is equals to 1 cp dt. Now next we can say this as also again, since volume is changing but the pressure is remaining constant, so dw dash is equals to pdv. Now in this case volume is changing, so pdv is not a zero value, and p is having some constant value, since, so this whole dw dash could be taken as a specific value. But if the constant pressure is maintained, what are the things going on? There is a little change in the corresponding internal energy. So the internal energy could be taken as du dash, since it is taken as to be change in internal energy. So by first law of thermodynamics, we can write it as dq dash is equals to du dash plus dw dash. So dq is cp dt, du dash be du dash plus p dv. So on this could be taken as equation 3. Now the condition is, since the rise in temperature of gas is same, means we are heating in this case also and we were heating in that case also. In both the cases, let the temperature be same, the difference in temperature be same. So in this case, if uh, let me write this in a manner that if the temperature change is same, why are we taking this as to be same? To avoid complexity, to make it simple. So let it the temperature be, the temperature change be same. So since the temperature is changing, whatever changing is in the temperature is done, the overall internal energy change will also be same, means du is equals to du dash. And initially du dash, our du means it was cv dt, so we can write it as cv dt, and we can put this in the equation above. So equation 3 becomes cp dt is equals to cv dt plus pdv. Now putting dt at one side, we get cp minus cv dt is equals to p dv. Let this be equation 4. Now from gas equation, pv is equals to nRT or mu RT, nRT, but n is taken to be 1. So pv is equals to RT, pv is equals to RT. So by comparing fifth and fourth, we get that Cp minus Cv is equals to R. Means specific heat at constant pressure and specific heat at constant volume is nothing but, means the difference between these two is always constant. Now if we divide this by molecular mass, so Cp by m minus Cv by m is equals to R by m. What do we get here? Just a normal equation, normal terms. So this could be written as Cp means for gram value, Cv is equals to R. And this is for 1 gram of mass. This was for 1 mole and this was for 1 gram. Okay. So this is what a mere formula is. Okay. Now next we will move on to the first laws of thermodynamics and its limitations. What are the things that first law of thermodynamics is not able to explain, or it cannot be helpful into? So first law of thermodynamics, so we will now discuss about limitations of first law of thermodynamics. So what are the limitations that first let us discuss that first law does not indicate, it does not indicate the direction in which the change can occur. So it does not specifies the actual direction from which the temperature change, the energy change, the internal energy change, or we can say whatever the changes are been taking place, that direction is not defined by this first law. It is always telling that this is proportional to that, this is proportional to that, this is related to that, but it's not all any time telling you that from which part to which part is the flow or is the change is being taking place. Second, that it gives no idea, it gives no idea about the extent of change. Means up to what extent, how much change will occur, this is not being told by this first law. Also, it does not gives no information on no information about the source of heat. Means you can say that it does not inform about the source of it, means where are we getting this heat, either it is from cold body, hot body. It is not been exactly told by this first law. So these are the limitations of first law of thermodynamics. After this we will move on to the second law of thermodynamics. What is this second law? Let us talk. So second law of thermodynamics.